Hello everyone, we are going to continue with the part 2 of the lecture for chapter 1. So we talked about chemistry, its central role, and the scientific process. So chemists usually define, or chemists like other scientists, they categorize research into two uh, categories. One is the basic research and second is the applied research. So I'm going to first start with the applied research, which involves studying a specific problem in industry or in the environment. And here is a picture of George Washington Carver. And everyone knows, or if you don't know, he worked with the peanuts, and that's an example of applied research. In his research with peanuts, he developed more than 300 products from the peanuts. So that's a direct application of his research, and that's the applied research. Whereas on the other hand, basic research is something that is done for the sake of the knowledge. People want to understand the phenomena, so why something is happening, and it may or may not find application or applications in the near future, applications directly, but the findings of the basic research in future may help to solve a big problem, or it can be applied to a specific problem in the industry or in the environment. So one such example of basic research is Dr. Gertrude Trude's aliens work, who worked with purines. If you studied biology, you know purines are the bases in our nucleic acids. So when she did her basic research with purines, this work now at that time was a basic research, but now this work has led to many applications in the pharmaceutical and medicine, pharmaceutical industry and medicine. So she worked with purines and studied the role in the cell of purines. So that's what the basic research. Over many years, it can become applicable to solve a bigger problem. So that's the difference. And now we are going back to chemistry, which is the study of matter and its changes. So we saw this definition before. Chemistry is the study of matter and its changes. And matter is something that has mass and volume, and because matter has mass, you can weigh it. For example, wood, sand, water, people, we all are matter, right? Everything is made up of atoms and matter. So here is the two terms that we usually talk about and do not want to get confused with. So one is mass and another is weight. So mass is the measure of the amount of matter in any object, okay? Weight, on the other hand, is the measure of the gravitational force on matter in an object. So measure of amount of matter and measure of gravitational force on the matter. So you see a picture here on the right hand side of an astronaut. So let's consider this is moon's surface. He's landing on the moon's surface. So the astronaut weight will change on the moon because the gravity of Earth and the moon is different. So he will weigh only 1/6 on the moon than on that of the Earth. So remember, weight varies with the gravity, mass does not. So let's take an example to apply the concept of mass and weight that we learned. So here's a problem which says the gravity on the planet Mercury is 3/8 that on Earth. What would be the mass of Mercury of a person? Mass on Mercury of a person who has a mass of 80 kilograms on Earth. Okay, so remember, what did I tell you about the mass? The person's mass would be the same because it is not related to the gravitational pull, right? The quantity of the matter will not change. So the mass will be the same as that of Earth, which will be 80 kg. But what would be the weight of that person? So weight, we know that depends on the gravity. So the person would weigh only 3/8 of 160 pounds. So if you do the fraction, you can either do 3 divided by 8 times 160, or you can calculate into decimal. So 0.375 times 160 pound will give you 60 pounds. So the force of attraction between the Mercury and the person would only be 375 times that between the Earth and the person. So it would weigh 60 pounds on the Mercury. So now we are going to talk about the properties of the matter. The first one is the physical property. Physical property is something that you can observe. Okay, so the properties of the substance that can be observed without changing the substance. So examples are color, mass, weight. So here you see copper wire, and here you see the iodine. So you can look at the physical properties of these substances. So another point about physical properties is these are the changes in appearances without changing the chemical identity or the composition. So for example, as I showed you that copper wire, now it does not matter if copper is made into wires or sheets or even as powder. The color of the copper or the appearance or the color of the copper remains the same, and its chemical identity remains the same. It is still copper, even though visually it can look like a wire or a sheet or a powder. It is still the same. So here's a table which tells you about the examples of physical properties. The property is temperature. An example is water remains H2O even if it is if the temperature is changed. So at 0 degrees Celsius it will become a ice. At 100 degrees Celsius it will be a boiling water, but it is still water. Or for example, color. Sulfur is yellow and bromine is reddish brown, or copper was this bronze copper color, right? Or taste. Acids are sour, bases are bitter. Or boiling point, water boils at 100 degrees Celsius. Or density. Density of water at normal temperature is 1 grams per mil. Or density of gold is 19.3 grams per cubic centimeter. So these are the physical properties. Chemical properties, on the other hand, changes the chemical composition of a substance. So it becomes something else after undergoing a chemical change. So chemical properties are those properties of the substance that can only be studied by forming new substance. It changes into something else. So for example, iron, the metal iron is iron, but when it rusts, it forms rust because now the iron combines with oxygen to form iron oxide. and now iron is no more just iron, it becomes iron oxide. Or for example, carbon, it burns, so it will combine with oxygen to form carbon dioxide. Or silver gets tarnished, becomes blackish in color after it combines with sulfur to form silver sulfide. So its chemical composition is changed and it becomes a new substance. That's how you study the chemical properties. Physical changes are defined as changes in which the chemical identity of the substance is not changed. So like physical properties. So the physical changes would be melting or freezing, evaporation. So water melts or water freezes, right? But it's still visually it becomes different. On melting it becomes water, which is liquid, and on freezing it becomes an ice cube, which is solid. So there's a physical change, but the chemical identity is not changed. The substance is still water, even if it is liquid or a solid. So physically the state has changed, the state of matter has changed, solid to liquid, but it's still the same water. So let's classify matter now. So matter is classified as a solid, liquid, or gas. And a solid is something that has a definite shape and volume. A liquid has a volume but does not have a definite shape. It takes the shape of the container. And gas, on the other hand, does not have a volume or a definite shape, does not have a definite shape or volume. So it takes the shape of the container as well. And here's a diagram which gives a good visualization to imagine solids, liquids, or gases. So here is a block of solid, and you see how these atoms are organized in an orderly manner. They're so compact or so close and tightly packed together that it gives a fixed shape to a solid. And then you have a liquid where the atoms or molecules are not so orderly packed as solid. They are close together but not as close as solid, right? You see there is some empty space in there. So they are able to move around, and that's the reason why they can take the shape of the container. They do not have the shape of their own. And here is a gas cylinder, and if you have to show it in the model, you see in gases the particles are far apart, and according to a kinetic molecular theory, which we will study later in the chapter, later in this course, you will learn that these particles are always in a rapid random motion. So they are far apart, so they do not have a definite volume or a definite shape. Here is another classification of matter. So all matter can be classified as a substance or a mixture. Substances can be classified as elements or compounds. And element is something which is made up of the same atom. Okay, so here is an example of a gold coin, and you see how all the atoms of gold are packed together. So you're also seeing a molecular view of gold. Then compound is made up of one or more than one element. So here's an example of water. Water is made up of 2 hydrogen atoms and 1 oxygen atoms. So you see a molecular view of water. So compounds is made up of 2 or more. Then we come to mixtures. Mixtures can be defined as homogeneous or heterogeneous. Homogeneous mixtures is there's still 2 different elements, but they are mixed together. So here you see these rings which look homogeneous to us, but when you look at the molecular view, you see gold and silver is mixed in making these rings. So they appear homogeneous, same, but when you look at the composition, it is made up of more than one type. So example can also be if you put salt in water and you mix it up, you can't really separate it visually, right? And then the heterogeneous mixture, as it says hetero, so that means you again see more than one component there, right? So here is an example of heterogeneous mixture. So this is a prospector's pan, and they are basically separating the mixture of gold flakes in water, right? So this is water in the molecular view, and the yellow balls are representing gold, and the other red and gray is the water molecule. So it can be separated even visually, you can see here as well. So again, I'm gonna go over those things. So elements are composed of one type of atom. An atom is defined as the smallest particle of an element. Elements are represented by chemical symbols, and they are also represented in the periodic table of elements. So if you open your book, you can always see a periodic table in chemistry which lists all the elements, and you will also see the names of the elements and the chemical symbols. So examples are Cl, which is the symbol for chlorine element. H is a symbol for hydrogen. Mg is a symbol for magnesium. Similarly, O is a symbol for oxygen, N is a symbol of nitrogen. So these are some of the elements. Compounds, on the other hand, as I said before, are made up of two or more elements, and they're chemically combined. So example is NaCl, where you have sodium, which is an element, and Cl is chlorine, so you have sodium chloride, which is salt, or you have water, which is made up of hydrogen and oxygen, or you have a molecule of sugar, which is C6H12O6. So you have 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen. So that is how the compounds are represented. And many compounds, they can exist as a group of atoms bonded together as a unit, and these units are referred to as molecules. So for example, oxygen molecules, so O2 will be made up of 2 oxygen atoms. So two atoms can also form a molecule. So let's look at this conceptual example. So here you are given a list of certain elements and compounds, and you are being asked which of the following represent elements and which of them represent compounds. Now remember, elements are either represented by a capital letter or they are represented by a capital letter followed by a lowercase letter. So for example, I showed you magnesium, right? So for example, in magnesium, element is made up of Mg. Or you saw chlorine, that was made up of Cl. It's still an element. And compound, you know, will have more than one atom. So let's look at this example. First is only C, so that is a symbol for carbon. Cu is a symbol for copper. H, you know, is hydrogen. I is iodine. So that is not an element, it's a compound. So let's circle the compound. Bn again has boron and nitrogen, so that's again a compound. In is indium, so as I said, first capital letter followed by a lowercase is a element. And then you have hydrogen, and you have Br, which is a symbol for bromine. So HBr is hydrobromic acid. So sorry, it should be a circle. So it's a compound. So you are expected to memorize the names, the symbols of at least the first 20 elements in the periodic table. So start familiarizing yourself with that, and then you will also learn a few as we move along, but the first 20 are must. Okay, so the solution is here. We already went over the problem. So HI, BN and HBr are composed of two symbols, so that's why they're representing the compound. Carbon, copper and indium are representing a single element. Let's talk about mixtures. As I said, mixture is a physical blend of two or more substances. We talked about homogeneous mixtures, which are uniform in composition, example salt and water. And then the next type was heterogeneous, which is not uniform in composition. And that would be something like sand and water,